Good afternoon. In today's video, we will be looking at the u-substitution strategy for integration. Okay, so as you know, u-substitution is used as the chain rule equivalent of integration. And it is a highly requested topic, so that's why I've decided to make a video on it. And it really has some tricky parts to it, so we're going to be looking at it very closely. Okay, so just to recap, the chain rule says that the derivative of a function in a function, or a composition f of g of x, is going to be the derivative of the outside times the derivative of the inside. And this right here is the basis of the chain of the u substitution. Okay, so what I want you to notice is that here we have g of x, and here we have g prime of x. So one thing, the hardest part about chain rule is actually figuring out when to use it, right? Because doing it is not really that bad. It's just figuring out, identifying when u substitution is going to be useful. So that's really what I'm focusing on right now. You see here that there's a g of x and a g prime of x. This is what I refer to as the derivative antiderivative relationship. We have a derivative and an antiderivative. Once you see that you have that connection, it's very likely that you're going to be using a u substitution. So look for that. The next thing that I want to talk about is what's actually going to be your u. What do you substitute? Because here we have an f, we have a g, and a g prime. So it's hard to figure out what's going to be your u. Well, your u is always going to be your g of x. It's always going to be your inside function. Okay? So that right there is enough introduction to then get started with some examples. All right, here we have our first example of a u substitution. Here we're looking at the integral of e to the sine x cosine x dx. You'll notice that we have sine and cosine. This right here is a great indicator that we're going to be using a u substitution because you have that derivative antiderivative relationship. Cosine x, well, that's the derivative of sine x. So we have some place to start. Okay, so now you ask yourself, which one is going to be your u? Your e, your sine x, cosine x? Well, the answer is simple. It's going to be the sine x. I'll tell you why. U equals sine of x. Okay, and it's because sine of x is your inside function. Sine of x is embedded in your e to the x. So that's telling you that sine of x is your inside function. Like how g of x was your inside function, now it's going to be sine of x. Okay, so we could make that substitution right now. We could just make that e to the u, but that wouldn't be enough because now we're mixing u's and x's. No good. We've got to get everything in terms of u. Okay, so the next step is to handle that dx. We're going to rewrite that dx in terms of u's. Okay, so what we can do is we can say that du dx equals cosine of x, just by taking the derivative of your u expression. Okay, now we can rewrite this to say that du equals cosine x dx. Okay, great. We're getting there. Now what we need to do is divide your cosine over to get dx equals du over cosine of x. This right here is a very important step because now we're going to substitute dx back up here. So instead of dx, now we have du over cosine x. Okay, I'm just going to pause here for a second to show that you don't have to go through all of these steps to get dx equals. Because if you just remember that dx equals du over the derivative of u, that is, you'll be fine. So just to reiterate, dx equals du over derivative. Okay, so that's something there to memorize. Just remember, dx equals du over the derivative. That's going to make that substitution a little bit easier. You don't have to go through the steps to figure out what dx is. Okay, so now we have e to the u cosine x du over cosine x. Well, you'll notice that cosine x divided by cosine x is just 1, so we can cross those out. So all of this brings us to the integral of e to the u du. Now that everything is in terms of u, we could just integrate normally. As we know, the integral of e to the x is just e to the x. So for this e to the u, it's still going to be e to the u plus c. Plus c because that's the constant of integration. Whenever you're doing an indefinite integral with no bounds, you've got to add your plus c. All right, so are we done? No, because the question is asking us for the integral of e to the sine x cosine x. We made up u, right? U is a creation of ourselves to help us solve this problem. U, as far as the grader is concerned, does not exist. So we have to put everything back in terms of x. All right, so to do that, we're just going to say, okay, instead of e to the u plus c, it's going to be e to the sine x. So e to the sine x plus c. And that right there is the answer. Okay, let's do another one. And probably there'll be people that do this that actually FOIL this out 4 times, multiply by 3x squared, and then just do power rule. You could do that, but don't, because there's a better way. All right, so what we could do here is say, all right, we have our x cubed plus 10, and here we have a 3x squared. Well, the derivative of this expression here is just 3x squared. So there we have it. We have a derivative-antiderivative relationship, which means that it's good to go for u substitution. Since this right here is what's considered the inside function, that's what I'm going to make the u. So u equals x cubed plus 10. Next step is to figure out what dx equals. Dx, if you remember, is du over the derivative. So dx equals du over 3x squared, the derivative of u. Okay, now that you have these two things, you're ready to make all your substitutions. So this right here becomes u, and dx becomes du over 3x squared. I'm just going to rewrite that a little bit nicer. We have 3x squared u to the 4th du over 3x squared. Okay, now what we can do is cross out those 3x squareds, and we're just left with the integral of u to the 4th du. Okay? To integrate that, we'll just get 1 over 5 u to the 5th plus c. But can we leave our answer like that? No, we can't, because they didn't give us u. We have to leave it in terms of whatever variable we start with. So I'm just going to make that necessary adjustment. We'll have 1 over 5, what was it, x cubed plus 10 to the 5th plus c. And there you have it, u substitutions. All right, so the first thing that I'm looking for is if there is a derivative-antiderivative relationship. That's going to tell us that we're doing a u substitution. So here I see an x squared, and here we have an x by itself. Well, a 4x. So that's telling me that we do have that relationship. Okay, so the next part comes to choosing your u. The u that I'm going to choose is going to be x squared plus 1. The reason I'm choosing x squared plus 1 instead of just that x squared is because if I were to just choose the x squared, all that happens is that I'm still stuck with a u plus 1, right? I'm still stuck with something inside of a square root. I'd rather just take the entire thing. That's usually the best bet. Okay, so u is your x squared plus 1. Dx is du over the derivative, so dx is du over 2x, and now we're ready to make all the substitutions. Okay, so that's going to give us the square root of 4x over the the integral of 4x over the square root of u times du over 2x. Okay, and you'll notice that those x's cross out. If they don't, you did something wrong. So make sure they cross out. Okay, so cross out your x's, and we can also simply reduce that fraction a little bit. We have 4 over 2, that's just 2. So putting this all together, we're back at 2 times the integral of 1 over the square root of u du. Okay, so this is a good question because now we have to integrate 1 over the square root of u. So whenever you're dealing with something like this, it's always best to put in fractional or negative exponents. Always best to rewrite it as an exponential, as a polynomial. This way you'll be able to use power rule. So as we know that 1 over u squared is just the same thing as saying u to the negative 1/2 du. Okay, so then that just makes it a lot nicer. We'll just have 4u to the 1/2 plus c. But can we leave it like that? No, we can't. We've got to rewrite it in terms of x. So since u is x squared plus 1, it's just 4x squared plus 1 to the 1/2 plus c. And there we go. We do have another example with an indefinite integral, and then there's one that I want to do that has bounds, just so that you can see what that would look like. All right, here we've got the integral of cosine x divided by sine squared x dx. So here we do have a derivative-antiderivative relationship with your cosine and sine. But now it can be a little tricky as to say, okay, which one is actually my u, right? Because you could kind of go either way with it. There is an answer. And it's going to be that u is going to be sine of x. The reason I'm choosing sine of x is because sine right there is inside a square. Okay, it doesn't really look like it, but it's really sine of x squared, which makes it now an inside function. It's inside the squared. right? So because it's an inside function, I'm going to go with that for my u. The next step is to get your dx equals du over the derivative, so du over cosine of x. Now we make all the substitutions. We're going to have the integral of cosine of x over u squared times du over cos x. Right. This last example is not quite a u substitution, but it involves a lot of the same strategies that we've been working with. This one asks you to rewrite everything in terms of y using this substitution that they give you. And when it says everything, it means everything, including the bounds. Okay, so let's begin. I'm going to start off by figuring out what is our dx in terms of y. Let's get that out of the way. So to do that, we're going to have to take the derivative of this expression, of this equation. Okay, well, square root of x, that's the same thing as just x to the 1/2. So taking the derivative of that will end up being 1 over the square root of x on the left-hand side, equaling, well, it's going to be cosine of y, because derivative of sine is cosine, but we have to multiply by the derivative of the inside, because that's a chain rule right there. So it's going to be cosine of y times dy dx. This right here, by the way, is an example of implicit differentiation. There's a video on that coming very soon. Okay, so next thing that we're going to do is actually isolate that dx. So that'll end up being dx equals the square root of x cosine y dy. This right here is the first substitution that we'll make. All right. So just to keep track, I'll just rewrite what we have. It is the integral from 0 to 1/2 of the square root of x over square root of 1 minus x. And instead of dx, it's now the square root of x cosine y dy. The next thing that we're going to do is replace all of our x's. Because here we have 1, 2, 3 x's that we have to rewrite in terms of y. Okay, so since we know that the square root of x is equal to sine of y, we could solve for x by squaring both sides. And we'll just get that x is equal to sine y squared. Okay, great. And also we know that square root of x is sine y, so we can make that substitution as well. So that'll leave us still 0 to 1/2. We haven't gotten to the bounds yet of sine y over square root of 1 minus sine squared y times another sine y times cosine y dy. Okay, let's keep going. From 0 to 1/2 of sine squared y over the square root of 1 minus sine squared y. Okay, so we can't just take the square root of that as it is. It's kind of stuck. But there is something that we can do. So if we recognize that, since we know that sine squared x plus cosine squared x equals 1, that's a Pythagorean identity from algebra 2, we can just say that cosine squared is equal to just 1 minus sine squared x. Okay, well, that's a substitution that we're going to have to make. So instead of saying 1 minus sine squared y, I'm actually going to rewrite that to say cosine squared y. Those are equivalent expressions. Okay, and that's still times cosine y dy. Okay, just keeping it going. We've still got 0 to 1/2. We haven't done the bounds yet. Of sine squared y over, well, the square root of cosine squared, that's just cosine y times another cosine y dy. Okay, you'll notice that those cosines just cross out. So all of that is equal to integral from 0 to 1/2 of sine squared y dy. Okay, but not exactly, because we haven't touched those bounds. We've rewritten everything in terms of y except for those, so we have to handle that too. These right here, those 0 and 1/2, those are x values, not y values. Well, we know that since the square root of x equals y, I'm sorry, not equals y, equals sine y, we'll have to figure out what y is. Let's start with 0. Okay, so square root of 0 equals sine y. This is going to be our lower bound. Well, 0 equals sine y. We know that that happens when y equals 0. Okay, so we have the lower bound. That's 0. That's nice that it doesn't change. Now let's do the upper bound. The upper bound is 1/2. So square root of 1/2 equals sine y. Well, if you remember from trigonometry, that's just when y equals pi over 4 radians. All right, so we have our lower bound is 0 and our upper bound is pi over 4. put it all together, and we get the integral from 0 to pi over 4 of sine squared y dy. Fortunately, they don't ask us to actually evaluate that because that would have been a whole lot more work. They just ask you to rewrite the integral. Thank you for watching and comment any suggestions for future videos.